Okay, so welcome everyone in another interesting topic in which I'm going to discuss the vibrational spectrum, which is the branch of atomic physics, atomic and molecular physics. So, the title of the discussion is Vibrational Energy Levels. Okay, vibrational energy levels and vibrational spectra. This is very much interesting topic for the atomic as well as molecular physics. Okay, so vibrational spectra of a diatomic molecule. Let us first discuss vibrational spectra of diatomic molecule. Okay, so that our understanding will be simpler. So let's discuss what is the vibrational energy. You are very much well aware about the vibrational energy as you have studied in solid state physics the lattice vibration, where you have considered the two lattice separated by some distance are going to be bounded with some elastic bonds in between them, so that any one of the particles displacement causes some motion along the line joining the two particles to consecutive particles. And you have considered the two particles or lattice points are joined by some elastic forces. Okay, so elastic spring, by considering elastic spring you have derived the derivation of the vibrational energy by applying some sort of uh, mathematical procedure, and you have arrived the vibrational energy as well as vibrational frequency. Okay, all of this was done in the solid state lecture or solid state physics, but here I am interesting to discuss the spectra originating from this vibrational energy. The same thing is happening in the molecule, where inside a molecule, at first case, we have to assume the molecules, the atoms are connected by some elastic forces between them. It is the most simpler case, as you have noticed in case of lattice vibration. Okay, so at first it was thought that diatomic molecule, the two atoms were separated by some elastic forces and elastic bonds are present between them, so that any one of the atoms displacement causes some motion which is directed opposite to the movement of the particle along the line joining them. Okay, so without wasting any time, let us first give the introduction about this. Here we have considered that the vibrational motion of a diatomic molecule. Okay, so here we have to consider some assumption that the two atoms are separated by some equilibrium distance r naught. I must have to draw a separate image for better understanding. Okay, so this is some particle. So this is one atom, and this is some another atom present in the molecule, and these two atoms are joined with the help of some elastic bond between them. Okay, so this is the elastic bond and the equilibrium distance between them some are not. Now if somehow by applying some external energies to the system of the molecule, if some of the atom be displaced from this equilibrium position, so that we have to draw again the two atoms. Okay, this is the first atom, and this is the, suppose the second one is displaced to some distance, uh, and then by the separation, the separating distance now changed from r naught to some r. Okay, so by what amount of change in displacement occurred? So this is the amount of excess distance that is present between the two atoms by the application of some external energy or some other kind of sources. Okay, so the displacement becomes some r minus r naught. Now, as we have considered, the two atoms are connected by the elastic bonds, so the law of elasticity should be hold for the system, and the restoring force which must be applied to the atom, second atom, due to the displacement of its equilibrium position must be directed to the opposite of the displacement, and we can easily write that F is proportional to this displacement with a negative sign present in front of the distance, the amount of excess distance. Okay, so if we remove the proportionality sign, then we must have to apply some constant k along with the negative sign, and the expression remains intact. But here you have to notice that k is positive constant, and we are very much well aware about this constant. This is known as the stiffness factor or the force constant, as you may call it. Okay, from the concept of SHM you are very much known about this fact. So this is not the newer thing in this discussion. Okay, now let us consider, this is too much long expression, so we have to consider this to be equal to some x, so that the expression will be get simpler form. F is equal minus kx. Okay, this is some simpler thing to do. Now here the interesting fact is that suppose the two atoms have the masses m1 and m2, and from the laws of classical mechanics you know that these two masses will be equally equal, or most probably contributing to the uh, force. Okay, the contribution of m1 and m2 both are applicable to the force acting between them, and you have to consider some sort of new mass which is called the reduced mass, which is coming from these two masses, as you know from the classical mechanics. This is not the new thing to do here. We have to consider the reduced mass which is resulting from the two masses m1 and m2, so that the system will be considered for better treatment. Okay, so if we apply the same mass to the system, then the reduced mass will also be equal to the mass of a single particle. If this mass be m, this mass be also m, then the mass resulting to m, this m by 2, I think. Why? Because mu is equal m1 m2 by m1 plus m2. So by considering the equal masses, the overall contribution to mass will be m by 2 m by 2. Yes, this is the reduced mass. So by considering also the same masses, the amount of mass contribution is not the same as you have considered the two mass. The mass will be m by 2, so reduced mass is more important, and the derivation of reduced mass you have already covered in the classical mechanics series. Okay, so I am not doing the derivation here. I must have to apply the expression gained from the knowledge of the classical mechanics, that the reduced mass of the system, of the composite system m1 and m2, will be nothing but m1 m2 divided by m1 plus m2. So let us put some equation number, so let me put this to the equation 1, let me put this to equation number 2, and let me put this to equation number 3. So here all the equations are uh, get simpler form, and here nothing new thing is done, as you may notice here. So at first we have to consider the elastic forces between the two atoms in a diatomic molecule, and the force resulting due to the displacement of one particle is nothing but proportional to the amount of displacement, and its direction will be opposite to the displacement, as is known from the Hooke's law. Okay, so let us proceed. Now, again from Newton's law of motion, we know that force is nothing but mass into some acceleration. Okay, now the amount of displacement we have considered here x, so the velocity will be dx dt, you know it very well, and the displacement will be d2x dt2, sorry, and the acceleration will be d2x dt2. This is nothing newer thing to do. So again the mass contribution is now changed to the reduced mass, so m must be replaced by mu, and the equation becomes f is equal some mu into d2x dt2. Okay, and put this equation number 4. Now by equating 2 to 4, this is also the force, this is also the force acting for the system. So by equating 2 and 4, we can easily get mu d2x dt2 will be nothing to minus kx, and by changing some modification, you will able to get d2x dt2 plus k upon mu into x is equal 0. Now this is nothing but omega square. From the knowledge of SHM or simple harmonic motion, you know that this is nothing but omega square, where omega is nothing but root over k upon mu. What is omega? Omega is the angular frequency corresponding to the oscillation of the system, originating due to the displacement of one particle from its equilibrium position. Okay, all the things are now crystal and clear. I hope so. So let's write it in the better way, that omega square x will be nothing but 0. Put it into a box. Okay, so let us name it as equation 5. Okay, now this is the angular frequency of oscillation, which is nothing but k upon mu. Now what about the corresponding linear oscillation? If we consider the corresponding linear rotation, linear frequency to be nu, then this will be this, and k upon mu, nu will be nothing but 1 by 2 pi root over of k upon mu. This is nothing but the linear frequency corresponding to the simple harmonic motion. It is interesting to note that as we have considered the elastic forces acting between the two atoms, and elastic bond is present between them, we have applied the Hooke's law, and we have applied the equation number 2 for this case, and by applying the equation number 2, we are able to get the frequency to be nu naught is 1 by 2 pi root over k upon mu. Okay, put it as equation 6. Okay, now this is similar to the case of classical mechanics. Now we have to apply some sort of quantum mechanics here, because this is the part of quantum world, as you are uh, well known to the fact that atoms do not obey the classical mechanics. Some sorts of law may be applicable to them, but the better thing is to apply the quantum mechanics to the system, as this is the part of quantum world. Okay, and for the higher order of quantum number, you are known that the quantum mechanics tends to the classical one. For h tends to 0. Okay, so this is the another thing, but we have to apply some quantum mechanical treatment here. But the quantum mechanical treatment is also the similar to the classical one, because this expression corresponds to the classical equation, and it is come from Anfer's theorem that the laws of quantum mechanics will be similar to the sort of classical mechanics, which is given from the Anfer's theorem. Now, we know that the uh, force corresponding to the potential can be expressed like this manner. So from this we can apply the potential, we can find out the potential energy of the system. So what amount of potential energy gathered due to the change in displacement, the work is done due to the change in displacement, and this work done remains stored in the system as the potential energy. So from equation number 2 we can write minus dv dx is nothing but some minus kx, so that dv will come to be kx dx, and this can be obtained from integrating. Let us suppose the potential is increased from 0 to v, due to the displacement of 0 to x dx. So by integrating you will able to obtain v is equal half k x square. Okay, so put it in the box. This is very important expression to work out further. Oh sorry. Okay, put it as equation number 7. Okay, now since this is the part of quantum world, we have to apply the uh, like the Newton's law of motion in case of classical mechanics, we have to apply the Schrodinger equation for the quantum mechanics. So we have to apply the time independent Schrodinger equation here, because I am calculating the simpler problem here, the Schrodinger equations, which is the time independent. Okay, and also in 1D we have considered the one dimensional motion. You have to notice it carefully that only the either the displacement taking place along this direction or taking place in this direction. So I have to say that this is the one dimensional motion. Okay, so since this is the one dimensional motion and one dimensional system, we have to apply the one dimensional time independent Schrodinger equation, which is nothing but d2 psi dx2 plus I'm doing the short of rearranging the Schrodinger equations, okay, so that the time will get consumed. Uh, E minus Vx into psi, which is also a function of x due to the one-dimensional problem, okay. So this is the time independent one-dimensional Schrodinger equation, and put it as equation number 8. Now we have find out the expression of potential energy from equation 7, and we can easily write the expression here, so that our new expression becomes d2 psi dx2 for this system 2m by h line square e minus half kx square psi is equals 0. This is some equation number 9. Okay, now this is the equation that I have obtained. If you have forgotten, this is the same equation that I have obtained while discussing the linear harmonic oscillator problem in the series of quantum mechanics. You can remember that in quantum mechanics I have already solved the linear harmonic oscillator problem. So if you have forgot, then I will paste the lecture to the I button present above the screen. Okay, this was a lecture, and in this lecture I have discussed the detailed derivation of how the energy eigenvalue and energy eigenfunction can be calculated from the potential corresponding to the linear harmonic oscillator. And this is and some numerical approach to this method is also present. um, if I'm not wrong, this yes, no, not this one. I hope yes, this one. This was the numerical approach to solve the linear harmonic oscillator problem, and in this case also we have encountered with the same potential and same uh, and we have obtained the same energy eigenvalue and same energy eigenfunction, but this is the numerical method and this is the analytical method. So both the videos I will paste on the I button present in the screen so you can find out easily. So let's back to our present lecture, which is okay. So I'm not doing the derivation of energy eigenvalue equation. Sorry, energy eigenvalue. I am only writing the expression of energy eigenvalue obtained by solving this Schrodinger equation. So the solution is given to the I button present in the screen. Don't forget to watch if you have uh, not remembering. Okay. So the energy eigenvalue obtained while solution is nothing but P plus H nu naught. Now let me explain. In the lecture that I have told you, we have considered here n, which is the quantum number corresponding to the problem. But here I have considered the V as a vibrational quantum number. Vibrational quantum number. Okay. So here we have to replace n to be phi, and nu naught is what? Nu naught is the linear frequency that I have obtained in equation 6. Okay, and v is the vibrational quantum number which can have the value 0, 1, 2, 3 and so on, integer value. Okay, now so the potential as gained from the equation 7, I have to plot it. Okay. Okay. So let us try to plot in the software present here. Yes. Sorry. I have to arrange some value of k. Okay. Okay. Let me um okay, so this is very much similar. Okay, similar expression I have to write. So this is very much similar to the expression y equal to x square, some sort of 2x square. Let us suppose k is 4 and y is equal to x square. So let us try to plot it. The plot will be the same. Okay, so yes, yes, this is the yes, this is the plot regarding this figure. Yes, so the equation 7 can also be plotted by a similar way, like mm, and parabolic shape is not present. Okay, I have parabolic shape is not present, so I must have to draw it in my own hand. Okay, this has flattened. uh, just wait. Sorry. Yes, more or less beautiful picture I have drawn. Okay, so this is the potential corresponding to half kx square, and the energy level can be drawn like this. We are well known that this corresponds to the energy level like this, which is some discrete in nature. So this is a quantum mechanical linear harmonic oscillator problem. So this is okay. Um, all some sort of energy levels I have to draw. Okay. Look carefully that the energy levels are equally spaced. This corresponds to half h nu naught as obtained by applying V to 0. So E1 will be, or E0 will be, half h nu naught that I have drawn here. Not the 0. E0 is not the 0. This is noted. This has to be noted. This is a more interesting fact that E0 is not the 0. That is the ground state energy corresponding to the linear harmonic oscillator is not the 0. This thing is already discussed in the previous lecture. So I am not interested to discuss here the same thing, but rather we must proceed here. So E1 by applying V to 1, we will obtain E1 is equal 3 by 2 h nu naught, and this corresponds to that this level. Sorry, 3 by 2 h nu naught, and similarly this by applying or putting V as 2, we will obtain 5 by 2 h nu naught, and also we can get other energy levels as this is the sorry this is the 7 by 2 h nu naught. Okay, so note that the energy levels are equally spaced with the value h nu naught. So E, I have considered V here. V plus 1 minus EV will be nothing but V plus 1 minus V. Half of gets cancel out, and h nu naught will be h nu naught. So the energy levels are equally spaced. Okay, so by making the transition from this higher energy level to a lower energy level, this corresponds to the emission of the energy which is equal to some h nu naught, as because this is the energy difference between the two levels. Okay, so by making the transition from higher energy level to lower energy level, you must have to end up with some h nu naught amount of energy. But you can say that if a 7 by 2 h nu naught particle makes a transition to 3 by 2 h nu naught particle, sorry, 3 by 2 h nu naught level, then the corresponding energy will be become what, 7 by 2 minus 3 by 2 means 4 by 2, that is 2 h nu 2 h nu naught. But this transition is not possible because of the selection rule. Now what is selection rule? You know very well from the quantum mechanical problem in case of atomic physics that I have discussed. While discussing also Zeeman effect, you can notice that what is selection rule. Selection rule are the rules which must proceed while the transition of the energy from higher energy level to lower energy level. Okay, so the selection rule in this case is nothing but delta nu should be equal to plus minus 1. So an electron can make a transition from half h nu naught to 3 by 2 h nu naught or 3 by 2 h nu naught to half h nu naught, but not from half h nu naught to 5 by 2 h nu naught or vice versa. This transition is not possible, but this transition is possible. Okay, as because the selection rule tells us this fact only. So the amount of transition from n plus 1th level or v plus 1th level to vth level gives the energy of h nu naught, and this corresponds to the spectral line with the emission of radiation, and this spectral line corresponds to the consist with the all of these spectral lines are arranged in the spectrum, and we will get the vibrational spectra that originates due to the vibration of the atomic system of diatomic molecules or some other higher order molecules. Same thing will we will can also obtain while discussing 3D harmonic oscillator or 2D harmonic oscillator, but here for simplicity I have considered only the one dimensional harmonic oscillator problem, and we are able to end up with the energy obtained during the transition, which is nothing but h nu naught, and this is the constant. Now you have to know that this frequency line is a vibrational spectra which lies in the infrared region only. Infrared region only. Okay, so this transition is possible only in case of infrared region. The spectrum obtained lies in the infrared region. Okay. Okay. This was all the things that is quite simple, and the most of the things are discussed as in case of some classical mechanics and quantum mechanics, but not the every cases will be simple like this, not the system will be harmonic always, as because the first thing we have considered that the atom consisting are elastic bonds between them, and we have considered the elastic forces between them and are able to obtain the parabolic potential here, and we are also obtain the vibrational or harmonic oscillator problem, and from this harmonic oscillator model we are able to get the energy spectrum to be of the value of h nu naught, but not always this uh, simple or idealistic problem will be present in our system. Most of the problem, the system is not so simple as the simple harmonic oscillator, as because the main thing in the simple harmonic oscillator is a bond which is perfectly elastic. That is, it can be stretched or compressed to any extent. Okay, stretched or compressed to any extent, but in reality the bond present in the atoms of the molecule are not perfectly elastic. Perfectly elastic bond is not present always in between the atoms of a molecule. So the bond, if the bond is stretched to a particular extent, the elasticity may be lost and the bonds gets dissociate, and the atoms constituting the molecule will get uh, detached from the system, and the molecules dissociate into the atoms. So the vibration of such molecule will not be described as in case of simple harmonic oscillator problem. So in that case, the laws of simple harmonic motion will not be applicable. So what kind of law will applicable to them? We must have to encounter it. Now our next topic is uh, anharmonic oscillator. Okay, the previous one was the harmonic oscillator problem, which is quite simple and quite idealistic, but not every time we have to encounter the simple harmonic oscillator problem, because the bonds may not be perfectly elastic and these may get broken and the atoms constituting the molecules get dissociate, um, and we must have to modify our simple harmonic oscillator problem to this non-idealistic case and named it as anharmonic oscillator problem. Now, the interesting thing in this case that the potential energy obtained due to this is not the parabolic in nature that I have drawn in the previous cases. Okay, so um, okay, I have to draw. Let me copy this. Ignore the values of y and x here. Okay. Let me copy this so that our new drawing will be get simpler. Let me paste here. Okay. So this was the previous parabolic potential that we have drawn, but in case of anharmonic oscillator, the potential is not uh, parabolic in nature. The potential can be given. Sorry, what thing has happened? Am I audible? I hope so. Okay, so let us back to our discussion that the potential is not parabolic in this case. The potential will have to modified here. Now, PM Morse, scientist PM Morse was successful to derive an empirical expression regarding the non-idealistic case, that is for case of anharmonic oscillator, and the expression is known to be Morse function and can be given as VR as dE 1 minus e to the power minus a r minus equilibrium distance I have noted like r naught. Okay. So must have to write r naught. Keep in mind that r naught is nothing but the equilibrium distance that we have considered at the beginning of this lecture. So PM Morse was first to able uh, for giving the anharmonic oscillator potential function, which is known as the Morse function, which is nothing but Vr is equal d 1 minus e to the power minus a r minus r naught. What is d? D is known as the dissociation energy. That is the energy up to which the bond, above which the bond may broken may be broken between the atoms, and the atoms get dissociate from the molecules. So this is known as the dissociation energy. Okay, and what is about A is the constant for a particular molecule, that it may get varied. For HCl, A may have some value. For H2O, A may have another value. Constant for a particular molecule. So it may vary from compound to compound or molecule to molecule. R equilibrium is denoted by R naught, and R is the internuclear distance in staged or compressed case. Now, what kind of special case may be present? Special case if R is equal to R naught. What about this function? Let me check. This is the equation number 10. Then this will be some equation number 11. So if we place R as R naught, then V R naught will become d 1 minus e to the power 0. So 0. 1 minus 1 0. So at R is equal, let us suppose this to be R naught. I have to plot here R and VR along Y. So at R is equal R naught, this is potentially 0. Okay, and at r tends to infinity, d 1 minus, this term is infinity, so e to the power minus infinity, more or less. Now its value is 0, so this is nothing but d. Okay, now if this was the previous potential, then this will get some sort of shrink here, but 0 at R0, similar to the simple harmonic oscillator problem, but the right hand side is more interesting. At R tends to infinity, this gets to some, sorry, this will diverge to infinity and approach some upper boundary here. So if I draw some upper boundary, let me denote it in dotted line. Then this will correspond to the, sorry, dissociation energy, dE, and the potential function is not the parabolic one which was obtained in previous case, but the corresponding potential is, or modified potential is like this. This is known as the anharmonic oscillator potential, and the value at r tends to infinity of the potential is d, which is known as the dissociation energy. Okay, so now the solution of Schrodinger equation must be accounted here for this potential. So if so okay, okay, let me write. The Schrodinger equation is nothing but minus h line squared 2m d2 psi dx2, since it is again the one-dimensional problem, d2 x dt2 plus vx psi x is equals some e psi x. So by modifying this, d2 psi dx2 plus 2m upon h line square, e minus vx is nothing but 0. So in case of vx, we have to put the equation 11, as it can be also expressed as vx d 1 minus e to the power minus x. Okay, which is also supposed to. Okay, let me check y is equal 1 minus e to the power minus x square. Let me check if it is plottable or not. Sorry. check this if it is plottable or not. So hope this will work. Yes. So the range of x, want to increase the range of x. This is not possible. Okay. So if you are not sanguine to the curve, then you can apply the Python program to plot it, and the result will be the same that I have drawn here. So if we apply the potential, so if we apply the potential to be equal to this in case of Schrodinger equation, then the energy eigenvalue becomes EV will be the first thing that we have obtained in case of simple harmonic oscillator, but there is another term which is try to reduce the energy eigenvalue. This is the equation number, sorry, equation number 12. Okay, so energy eigenvalue obtained by the solution of the Schrodinger equation by putting the potential to be equal to the Morse function. Just see, by equating, okay, by equating the Schrodinger equation and applying the Morse function to the potential, we are able to obtain the energy. Now you may ask that how the energy eigenvalue can be obtained and what is the detailed derivation of it. So the detailed derivation of it is not the simple task to do, like as we have obtained in case of linear harmonic or simple harmonic oscillator, but it is a tedious task to do. So for application of the non-idealized system, quantum mechanical system, the Schrodinger equations become very difficult to solve. This is also have been discussed in the previous few lectures. So yes, I have already discussed that in some cases the Schrodinger equation becomes very difficult to solve and cannot be solved exactly that we can solve in case of finite potential box or linear harmonic oscillator problem, hydrogen atom problem, one body problem, etc. So in that case, we have to apply some approximation method. Now, what kind of approximation method are present? The variational principle, variational method, or WKB approximation method, and the perturbation theory. So the perturbation theory already discussed. So by applying some approximation method, this will be solved in another lecture series. But here we are interested mainly to the result obtained by the solution of the Schrodinger equation. So by applying the approximation methods to solve the non-idealized Schrodinger equation, we can able to obtain the energy eigenvalue equation, that is V plus half H nu naught minus half V minus half V minus not, this is plus, okay, so V plus half whole square H nu naught XC. Now what is XC? XC is the corresponding uh, anharmonicity constant, okay, and it has some small negative value, okay. So by putting xc to be 0, we will return to the idealized case, v plus half h nu naught. This is the same thing that we have encountered in last section, okay. Equation number, sorry, what is this, equation number 10, I think. Yes, this was the 10, this was the number 10 equation. So this is the energy eigenvalue equation for the simple harmonic oscillator, and by putting Xc is equal 0 in the anharmonicity energy eigenvalue equation, then you will also able to obtain the energy eigenvalue as obtained in the simple harmonic oscillator. Now what is Xc? Xc is the dissociation constant. Dissociation constant. Okay. Now let me draw the energy level from this energy eigenvalue. So for this I must have to plot some two-dimensional graph. So here I must have to plot R, and here I must have to plot V as a function as. The Morse function can be drawn like this. At R is equal R naught, this will be 0, and this will begin to increase and will diverge to infinity like this. Okay, and let me find some upper boundary. Let me draw like this the upper boundary, and let me draw this upper boundary by the dotted symbol. Okay, sorry. This, and let us extend the left hand side. So the right hand side will be this, and this is nothing but the dissociation energy that we have already pointed out in the figure drawn above. Now note that EV is what? Let me write another one. V plus H nu naught minus of V plus half whole square H nu naught X E. This is in joules. Okay, this is the equation number, let us say 13. Same as 12, but I have write it as 13. Now if we divide the energy by Hc, we will able to obtain this H nu naught by Hc. So H gets cancelled out, and we are only end up with nu naught by C, minus same thing is happening here also. So H gets cancelled out, nu naught upon C into Xc. This, now this has some special name. What is the special name? This is the uh, transition. Uh, this is a physical quantity more important for the transition. Okay, let me check. I can check this. Please give me 5 minutes. I can check this. Okay, so this is nothing but the term value, and this is known as the term value. Term value, and the term value can be denoted by GV and is written as V plus half. Now nu naught by C, this can be written nu naught bar. This is the notation. Okay, so nu naught by C is denoted by nu naught bar, and nu by C will be similarly can be written as nu nu bar, or here this is also nu naught, so this is nu naught bar into Xc. Okay, this is the equation number 14. Now let us find out the energy levels. Now without plotting the EV, we are interested more than term value GV, because this makes the transition, this gives the more accurate transition lines in the spectrum obtained due to the transition. So by putting V is equal 0, we can able to obtain G0, which is nothing but half nu naught bar minus 1 by 4 nu naught bar into some XC. Note that this is the same thing that we have encountered in case of simple harmonic oscillator, but by choosing anharmonicity, the is second term arises here. So if we plot it, this gives some value G0 and it will be non-zero. So let us say that this energy level will be correspond to this, note as G0 for V is equal 0. Okay, now for putting V is equal 1, by putting V is equal 1, V is equal 1, we are able to obtain G1, which is nothing but 3 by 2 nu 0 bar minus 3 by 2 9 by 4 nu 0 bar XE. Okay, so again this is the same thing that we are obtained from simple harmonic oscillator problem, but the new term is only due to the anharmonicity. And you can see that by increasing the value of V, the G levels gets shrunken. That is, uh, it will be very clear when we consider the more higher level. V2 G2 will be 2, that is 5 by 4 nu 0, and this will be the square of this 25 by 60. Okay, let me check 25 by 4. Okay, this is, yes, 5 by 2 whole square, and this is 5 by 2, I think. Yes, 5 by 2. So here also the first term correspond to the simple harmonic motion, but the second term only due to the presence of anharmonicity in the system. And you can notice that more higher levels, the more reduction of the term value happening. So the energy levels in this case is no longer equispaced, but gets closer for higher order of V. This is, if this is for G1, for V equal to 1, then this will be G2 for V is equal to, this will be G3 for V is equal 3, and more higher order correspond to the shrinking in the energy levels. Therefore, let me try to draw. Okay, more of this, sorry, G5, this is G6, this is G7, gets closer or increasing, gets more closer, gets more closer, gets more closer, gets more closer, and finally becomes continuous. Finally becomes continuous. Okay. Finally becomes continuous. Finally becomes continuous. Okay. Finally becomes This is the energy levels that is obtained for an harmonic oscillator. This is more important, and this is the present most of the cases, and the previous one was for idealized case. Okay, so this is more general. uh, Give the number to this as 15. Now let us draw some conclusion here. The selection rule is quite interesting in this case. So the drawing of the energy level, I must have to write that we have noticed that thus as V increases, that we have noticed from this, increases the spacing between the two energy levels, which is corresponding to vibration. So vibrational energy levels decreases, that is vibrational energy levels are no longer equally spaced. Equally spaced. So the selection rule gets also changed here, and it's quite interesting that it can make any transition from any level, provided the selection rule for delta nu should be, sorry, selection rule for delta V. The previous one, the selection rule, okay, so this is delta V is equal plus minus 1. Okay, so this is for V is equal, I hope, 1 0 1 2 3. V is equal 3 level to V is equal 2 level, V is equal 1 level, V is equal 0 level. Okay, so the selection rule was delta V is equal plus minus 1, that it can make transition from V is equal 3 to 2, 2 to 1, 1 to 2, 2 to 3, 4 to 3, this order. But here the selection rule is quite different. Here the selection rule is quite different, and the selection rule is given by delta V is equal plus minus 1, plus minus 2, plus minus 3, providing this should be the integer, the difference should be integer, that is, and you, this is the fact in general, that V is the integer, so the integer transition can also only possible, so it can make transition from 1 to 0, 2 to 0, 3 to 0, anything. Similarly vice versa, 0 to 1, 0 to 2, 0 to 3, while transition from higher energy level to lower energy level, energy is released and we will get able to get the spectrum corresponding to the transition. And note that now these are the okay, there is another thing which is quite interesting, that I must have forgotten, that while transition from V3 to 0, 2 to 0, uh, that is for higher order transition to ground state transition, these are known as the fundamental transitions, which are quite um, general in case of uh, anharmonic vibrational spectra. This is quite general, that it can make a transition higher energy level to the ground state. But as the increase in level, that is V is increased from V equal to 1 to V equal to 2, V equal to 3, more transition is possible. But selection rule provides that every transition is possible. So V is equal 1 to 0 is quite simple. This is known as the fundamental vibration or fundamental transition, 0 to 1 or 1 to 0 or 0 to 1. This is a fundamental transition. But V is equal 0 to 2, it is called first overtone. The transition is first overtone. Although this transition is also possible, but the name of this transition will be first overtone. Similarly, for 2 to 0, it is also known as first overtone. Now, V is equal 0 to 3 is known as second overtone. Second overtone. Similarly, for 0 to 3, sorry, 3 to 0 is also second overtone. Okay. Now, these are all about the higher energy state and ground energy state or ground energy level. Apart from the fundamental and overtones, there can be another kind of transition. Let me write this. There's apart from the fundamental and fundamental transition and overtone, there can be another transition. It is more interesting than the simple harmonic oscillator, another kind of transition, which is like V is equal 1 to V is equal 2. That is, the energy level uh, employed is not the ground state but two different energy levels, not including the ground state. V equal to 1 to 2, V equal to 2 to 3, etc. V equal to 2 to 1, V equal to 3 to 2, etc. They are referred to as hot bands. Hot bands. They are referred to as hot bands. And the transition including the ground state energy level are known as first fundamental transition and overtones. But the transition which is not including the ground state but including the two different energy levels are known as hot bands. But uh, they actually very weak band. They are called hot bands as because high temperature is one of the condition for high temperature is one of the condition for these for their origination. Okay, so hot bands happens when high temperature is present in the system. So this was all about the anharmonic oscillator problem, and the overall picture was given for the vibrational energy level and vibrational spectra for a diatomic molecules, which is very interesting topic. So I have chosen it to discuss in front of you. If you like, then you can press the like button and subscribe, and the videos related to this topic are pasted in the I button. Please check and follow this. If you enjoy it, then you can give the thumbs up. Okay, thank you very much for watching.